This is a complete engineering design study, carried out end-to-end by an AI agent, and so is the video you are watching, created exclusively through natural language prompting. No human opened a CAD program, meshed a model, or edited a video timeline. The mission: take a slot die coating head and make it as light as possible without breaking a single constraint. A slot die head spreads fluid from one inlet into a perfectly even curtain across 300 millimeters. Inside, a manifold, a diffuser, and a lip land, a slot just 0.15 millimeters high. The rules: uniformity within ±2%, lip deflection under 20 microns, safety factor above 2. The goal: minimum mass. Behind the study stands a complete open toolchain, orchestrated by Claude Fable 5 agents through the Model Context Protocol. Free CAD for parametric CAD, GMSH for FEM meshing, Calculi X as the structural solver, OpenFOAM 11 with Snappy Hex Mesh for CFD. Through an MCP server, the agent extended itself when the built-in tool proved too limited. ParaView for scientific visualization, running headless. Blender with cycles for photorealistic rendering, Matplotlib and Pillow for charts and slides, FFmpeg for video assembly, N8N and Telegram for notifications, and even the voice you are hearing right now was generated by the pipeline, using Piper text-to-speech. Pause on what that means. Everything in this project: the CAD model, the meshes, the flow and structural simulations, the optimization decisions, the renders, the written report, these slides, this narration, this film, was created purely by prompting AI agents in plain language. The human contribution, direction, decisions, and review. Nothing else. Construction happened in free CAD, driven by a parameter spreadsheet. Each iteration regenerated the solid, extracted the internal flow volume, and exported tag geometry for meshing. A showcase assembly was modeled too: 2 body halves, a brass shim defying the gap, 10 M8 screws. The assembly deserves a closer look. 2 machined body halves close around a brass shim, whose thickness alone defines the 150 micron gap. 10 M8 screws clamp the halves. The lip land runs dead straight across the full coating width. Every dimension is parametric. Change one cell in the spreadsheet, and the whole model, flow domain included, rebuilds itself. And this is the flow inside it, in 3 dimensions. Fluid enters through the central port, spreads along the manifold, and leaves the slot as a continuous, gap-free comb across all 300 millimeters. The geometry is stretched for visibility, depth 4 times, thickness 8 times. The real slot is thinner than a sheet of paper. Exit uniformity, ±0.45%, 4 times better than required. In motion, the principle explains itself. Particles race down the feed, slow in the manifold, and leave the lip as one even sheet, computed from the converged open foam field and rendered frame by frame in headless ParaView by the agent. Pressure tells the same story from the walls. Nearly the full 86 kilopascals fills manifold and diffuser almost unchanged, then collapses to 0 across the last 5 millimeters of lip land. That single, deliberate pressure drop is what irons the flow flat, and the measured outlet profile confirms it. The structure, shown honestly: Von Massey's stress on a 20 mm slice of the winning design, loaded with a CFD cavity pressure of 0.0882 megapascals. The peak is 13.6 megapascals at the lip root, safety factor 17. The bending view exaggerates deformation 3,000 times to make it visible at all. The real lip tip moves 1.87 microns, less than a tenth of the limit. That trustworthy FEM had to be earned. The first structural model reported a lip deflection of 5 nanometers, suspiciously perfect. The agent cross-checked with a hand estimate, found its simulation 1,000 times too stiff, rejected its own passing result, and remeshed with second-order elements. Corrected answer: 15 microns, 77% of the limit. The constraint that looked irrelevant was the active one. 4 iterations, each justified before it was simulated. Iteration 1, shorter diffuser, smaller manifold, mass down 46%, and the lip got 5 times stiffer, because a smaller pressurized cavity is a stiffer one. Iterations 2 and 3 pushed the diffuser to 35 degrees, legitimate in creeping flow. Gains shrank each step. The loop recognized the plateau and stopped. The winner, 1.05 kilograms, down 65%. Every constraint holds with wide margin, deflection at 9% of its limit, safety factor 17. This is the optimized head, and this is the channel inside it: manifold, converging shoulder, and a slot thinner than a sheet of paper. What is this worth in euros? 3 scenarios, honestly labeled. A single die redesign nets 2.5 to 13,000 euros per project. A service provider running 20 studies a year gains 50 to 300,000 euros annually. Pipeline payback in under 6 months. And a battery coating line, where scrap is the real money, 100,000 to 5 million euros per year. But that figure stays hypothetical until the readiness gaps are closed. The deeper finding is a cost inversion. Of the 300 to 900 euros one study costs, 60 to 80% is human review. Compute and tokens are marginal. The engineer becomes the reviewer of record. That is where agentic engineering is heading. And what it is not: production engineering. This is a prototype, readiness level 3 to 4. The fluid was Newtonian. Real coatings shear thin. No thermal analysis. No coating-bead simulation. No manufacturing constraints. 2 of 4 CFD runs hit their iteration cap. Every caveat is documented, with a path to close it. Today, this is a tireless junior simulation engineer, whose overnight work arrives pre-documented. Designed, simulated, optimized, written, narrated, and edited by Claude Fable 5 agents, 100% through prompting. Built on free CAD, GMSH, CalculIX, OpenFOAM, ParaView, Blender, Matplotlib, Piper, FFmpeg, and N8N. Connected by the Model Context Protocol. The full report, every number and every caveat, accompanies this video.